Okay, great. We're going to do a lot of context switching today between slides and examples, but hopefully we have time for all of it. So welcome back to lecture, everybody. It's a pleasure to have you all here. Thank you for coming. Today we're going to be talking about multi-threading in Rust with shared data. And you might be wondering, okay, is there any other way to do this other than shared data? It turns out there are other exciting models for concurrency that we'll talk about next week. But today we're talking about shared data, which is hopefully familiar to you from CS 110. So at the end of last lecture, Ryan brought up this example of the extroverts demo. And can somebody quickly recap what this demo was about and what it was showing? What was the weird issue that we saw at the end when Jerry's name just kept on popping up? What was wrong with this? Right. And Courtney, how would we fix that? Exactly, right? And we're going to see an analog of that in Rust, right? So in Rust, if we try this out, so I'm going to quickly, let's see, I think I have to swap my screen share now. I have to open the link for, oh my God, okay, so many things that have to happen. If I open it, and then I will share, bam, 1 second. Oh my God, too many windows. Get right back there. Okay, so now I'm going to open the playground. Do people see that? Right, so if we try to compile this, if we try to run it, it says closure may outlive the current function, but it borrows I, which is owned by the current function, right? And wow, the Rust compiler even tells us what we can do to avoid this issue, right? So it's essentially complaining that we are trying to pass a reference into the thread, and we don't know how long this thread is going to live, right? So remember, this kind of goes back to the lifetimes issue, right? That we taught, it was one of the first things we talked about in this class, and it's something that you should constantly be thinking about. How long is I going to live, right? Sounds like incorrect grammar, doesn't it? How long is I going to live? Right. So how do you know that your main thread? How do you know that you won't just spawn a bunch of threads and this function is just going to die, right? And you're referring to something that lives inside of this function, and now you have a dangling reference, right? That would be really bad. So what Rust is telling us is we have to use a special syntax with the closure. If I type in move here, what it's going to do is it's going to take the captured variables. So okay, I should rewind a little bit. In a closure, you have this idea of the arguments to your function go inside those two, kind of like pipes, those two absolute value signs in a way, right? These vertical bars. But everything that's referred to in here is sort of captured by reference in a way, right? So the nice thing here is that this has a static lifetime, presumably, so that it's going to live forever in some sense, or as long as it's the longest lifetime in the program. So we don't have to worry about referencing that, right? But this I right here, if we say move, what it's going to do is it's going to move I into the loop. And you might be wondering, okay, isn't that bad? Isn't it bad that we're moving our counter variable into the loop? What if we tried to reference it at some other point? Well, it turns out that's okay because remember, I is a usize, right? It's an integer type, and integer types implement the copy trait. And the copy trait means that the move semantics, when you move an integer, when you take ownership of an integer, it's going to produce a copy. Are there any questions about that so far? I think I said a lot. Any clarifying questions? Exactly. Yes. So these are all references, by the way. So we're not moving so in a way you can think of this as we're sort of moving the references inside, but we're not moving the strings themselves. The strings live over here and we can refer to them freely. But this I right here, this I is a local variable defined here. And we want to make sure we can actually move it into this context so that we don't end up having a reference to something that might have been dropped. Does that answer your question, Trip? Okay. So let's run this and let's see what happens. Okay, lovely. So we see what we expect. So we see Frank, Patty, Julie, Marco, and Lauren, and John, and we run it again, and we get to see their names in a different order. So there's some sort of non-determinism here, which is exciting. We don't know what the thread scheduler is going to do. It's kind of a fun game to see what's going on. Looks like there's a question. Okay, great, awesome. Thanks, Ryan. So that was that example. So I'm going to swap back over to the slides. We're going to context switch back there. And then let's continue taking a look at what other examples we might want to see, right? So any questions about move before I continue forward, or about how closures work in Rust? This syntax right here with the 2 vertical bars, that's a closure. That's an anonymous function. You might have heard of this idea of a lambda function before. In CS 110, you probably used this in the first assignment. For Kevin Bacon, you had to define a comparator function for lower bound. And that would tell you sort of like equality in a certain sense when you're looking for someone. Does that make sense? Great. Okay, all right, no, I'll pause. Does that make sense? So yeah, it's a great question. In Rust, the captures are implicit. So whatever variables you use, so for instance, I here is captured. I is captured here because it's just being used here. So the compiler can sort of infer what's going on there. And if you want, a reference versus a value versus a copy, you can define variables before you create your thread, and you can just capture those variables that might be copies of what you care about. And we'll see examples of that later. Does that answer your question, Drew?
And by the way, this in C++ is equivalent to self in Rust.
Right, yeah. You might want to capture, like if this is in a class, right, in Rust, or I don't know if class is the right word, but if we're implementing, functions for a struct and we have access to the self keyword, we might want to capture certain attributes of this struct, right? So I don't think we'll see an example of that today, but conceivably that's something you can do. So this move keyword says capture, so everything that I reference, right, like because I is referenced here, this move keyword says I'm just going to move this I, which effectively is a copy here, because I implements the copy trait, right? It implicitly figures out what we're capturing. You're asking maybe what if I pass in arguments here? So in this particular case, I don't think you necessarily would win much by passing arguments, because then in addition to spawning the thread, you'll have to also like figure out a way to supply those arguments in there as well. And presumably you need to like make copies of the arguments and pass them in. But in this part, later on in the lecture, we'll see an example where you can have closures that take in arguments. But that won't be used for this particular context for threading. That'll be used for like some more like functional syntax, I guess. But I guess like when it comes to threading here, in general, we don't like pass in arguments to it. Oftentimes it's like you like capture things. Within the scope of within the scope of the for loop, but also that are referenced within the closure, right? So if I had like threads, notice how threads is not referenced here, right? Threads will not be moved into this closure because I didn't use threads inside of the closure. Does that make sense? Exactly. Okay, perfect. Any other questions? Okay, if that's the case, we'll continue forward. So then Ryan was also talking about this ticketing agent demo, which is another classic CS 110 example. I saw that yesterday, I think Jerry talked about condition variables, so maybe he talked about this last week. But the idea here is that we have all these different ticketing agents. I don't know if this is a timely example because air travel is pretty down recently, but you got these ticketing agents, right? And they have this shared state, the remaining number of tickets, and while the remaining number of tickets is non-zero, you have to decrement it, you have to sell the ticket, maybe you'll take a break. It's unclear, right? And can someone, I guess, articulate what the issue is with the code as it stands? What could possibly go wrong? Yes. Exactly, because this decrement operation expands to multiple instructions, and because it expands to multiple instructions, you can sort of have them interleaved in a really bad way. Like I can try to decrement, like for two ticketing agents, right? I could try to decrement this count in the middle of your decrement, right? Because you never know when you're going to be swapped off the processor, and then somebody else is going to get a turn to deal with this shared data. Does that make sense to people? You saw this in assignment 3. You saw this in farm actually, but you saw it in a different context. You saw it in the context of signal handling as opposed to multi-threading, right? So in num available workers, I hope I can talk about assignment 3 because that was due yesterday, I think. In num available workers, right, you'd have this issue where your signal handler is going to increment it, right? And the rest of your code, your main thread, is going to decrement it. And if you don't block sig child effectively, then you could have these things happening at the same time and they can corrupt state and really bad things can happen. Similarly, it's not only, the other important thing is that like when you're making this check, this remaining ticket's greater than 0, you still need a lock, right? You still need to make sure that access doesn't get interrupted because there are funky race conditions that happen if you like make that check, you believe it's true, and then right after you make that check, it's invalidated by another thread doing something. So these are like the worst kinds of race conditions because you're just pulling your hair out and you're thinking like, why? What's going on wrong? Like I can't even replicate this. So yeah, does that make sense to people? What's wrong with this example? Okay, so then we'll move on to the next one. So let's look at our attempt in Rust, right? So I'm gonna open up some Rust playgrounds again. Let's see if we tried to write the same buggy code in Rust, if it would be as happy with us. So I'm going to open up another Rust playground, and then we're going to swap over to there. So I'm going to share that screen. Okay, great. So this is what it looks like in Rust. And yeah, you see we have this vec new, we push a thread, and then we have this ampersand mute remaining tickets. Seems okay, right? And this ticket agent function, what is it going to do? It's so because this is a reference, we have to dereference it while the remaining tickets is non-zero, or rather greater than 0. We will handle call, and then we'll decrement it, and yeah, let's see how Rust feels about it, right? And let's see. Great. Okay, so it does not feel good about it. It says, the argument requires that remaining tickets is borrowed for static. So first of all, there's this lifetime issue, right? We don't know if remaining tickets is going to live long enough. Before, when we were just moving the loop counter into the closure, that was fine. We were just copying it into the closure. We were just saying, oh, we're on this iteration. But now they need access to the same piece of data, and that's bad. So it's saying, help to force the closure to take ownership of I, use the move keyword. Interesting. Okay. Do you all think we should use the move keyword? Do you think that'll solve our problem? Why not? I see some people shaking their heads no. Why would the move keyword? Well, first of all, let's try to use the move keyword and let's see how it feels about that. It's like, the Rust compiler told me to do it. It must be right? I don't even need to learn Rust. I can just look at the compiler errors and I can just follow the compiler errors and they'll tell me what to do. So let's see what that does. It's taking its sweet time, as the Rust compiler is wont to do. It's doing a lot of checks right now.
It's actually running it.
Yeah, it actually is running it. Okay. Great. Wow, what do y'all think about that? we don't quite... This is kind of sad. We've got all these agents selling tickets and nothing is happening, right? Nothing's quite happening there. Great. Okay, what do people think about this? What's going on? Exactly. It's just taking a copy of it, right? So basically each thread is getting its own copy, and like while it's sitting on the processor, it's able to decrement it maybe a little bit or something, right? But it's presumably not able to do much, right? They're kind of like they don't have shared access to the same piece of data. So exactly as you said, they each have a copy. This is bad, right? So it's sort of like they're not even able to work together. It's really sad. That's the whole reason why we like threads, so they can work together, right? So this clearly doesn't work. So let's maybe look at a different attempt, right? So we'll go back here. Okay, instead of just passing it in, what if we just try to, let's see. What if we try to use ref cell and RC? Okay, I see there's a question.
Oh, that's
Great, okay, perfect, yes. Okay, so you might not remember ref cell and RC, and that's okay because we kind of glossed over it. We didn't have you have any practice with it. But just to refresh your memory, ref cell lets us delay the borrow checker checks to runtime so that we can have potentially multiple mutable references but at different times, right? And RC lets us have it'll let us have sort of this so the ref cell gives us something called interior mutability, if you recall that. And RC will let us have multiple references to the same piece of heap data. So it used to be that with box you'd only have one single reference, but now you can have multiple references. So I'm just going to open up this example. We don't have to go too far into the details of how ref cell and RC work because that's not going to be the focus of today. We're going to be talking about other smart pointers eventually. But just to show you what that would look like and how the compiler feels about it, we can see this right here. Do people see that? So I'm just going to quickly go over this. Actually, let's see. Is this right? Yeah. So we have this remaining tickets, right? And what I do is I'm going to say, I'm going to clone the remaining tickets, right? So I have this remaining tickets reference. I'm allowed to clone it because it's an RC, right? So this was, if you recall, our persistent data structure we implemented 2 weeks ago. It was a long time ago. Totally understand that. That was where we had the linked list that had multiple things pointing to it at different parts, right? I think so here what we can try is we can try making a new RC. We can put in a new ref cell, and then we're going to have them have references to the same piece of data now. This seems a little bit more reasonable, right? So let's see what the compiler thinks. So it's clearly not happy with us. It says, so what does it actually say? It says, this RC ref cell cannot be shared between threads safely. It's like, wow, how did it know that, right? How is the compiler able to figure that out, right? If we scroll a little bit further, we see that it says this trait called sync is not implemented for this, right? So now you're wondering, what the heck is this sync thing, right? And required because the requirements of this thing called send, right? So, okay, so it's saying, okay, certain traits aren't implemented for this, right? So just to foreshadow, what we'll talk about later is that Rust encodes its notion of thread safety using traits. And we talked about traits 2 weeks ago, right? Or so. And it's a really cool, powerful, flexible idea because this lets you sort of place sort of markings on different pieces of data and say, this piece of data is safe to share across a thread, for instance, right? But does this error make sense to people? What's going on here? What the issue is? Are there any questions about this? Just gonna pause. What do these traits bring that is thread safe? No worries. That's great. So that's a great question, and what I'm going to show you is that they bring nothing to show that it's thread safe. Basically, these traits are symbolic. They basically say, so this is another thing that has to do with unsafe Rust. So when you're actually implementing things like mutexes, which we're going to see pretty soon, you're essentially saying that, trust me, I did this implementation correctly, and because I did this implementation correctly, I'm going to mark it with this send trait, or I'm going to mark it with this sync trait to convince you that it is safe. And you can't implement this manually yourself for other pieces of data because that would require using unsafe code, presumably. Does that make sense? Yeah, so you're asking like what do send and sync bring? Nothing. They're marker traits. So this is a concept we didn't talk about yet. But there's this idea that you can have traits that mark certain properties and they only have symbolic value. But this is really cool because this lets you organize things in your type system. And this lets you sort of place constraints that you can sort of communicate with the compiler. Does that answer your question? Yeah, great question. Any other questions? Okay, so how do we actually fix this, right? So it looks like, yeah, sort of wondering if I should just like show the finished example or like maybe just like step by step show how we get there.
Do people have a good sense of why we need to use RC here?
Or why we need to use something like it. Right, okay, so what does RC give us? Exactly. It lets us point to like the same piece of shared memory that lives on the heap, right? So if we didn't have RC, right, the issue before was that we were just copying things into these threads. We need these threads to be pointing to the same thing. And at the same time, we need this thing to live long enough, right? So if we have something like RC, it's going to live as long as there's something pointing to it because it has this reference counting property.
In the very first example, we put 250, the number 250 on the stack, and then we passed references to the threads. And the Rust compiler complained because it said, well, hey, this value is living on this one thread stack, but how do we know for sure that this one thread is going to outlive all the other threads? If it doesn't outlive all of the other threads, then we have a problem because its stack is going to get destroyed and all these other threads have pointers to its stack, and now they're going to try to use that value and it's going to be gone, and that's not good. And this is different using RC because instead of allocating 250 on the thread stack, it's allocating it on the heap, and then it's keeping track of how many references there are to that heap memory so that it can free the heap memory when the reference count hits 0.
Yeah, so really you can think of this as like a lifetimes issue, right? Before we didn't know that if it was going to like live long enough, right? Now we're ensuring that it lives as long as something is pointing to it, which is good, right? That is a good question. Why don't we just make this a global variable? I guess the short answer to that is that global variables are not nice. We don't like to, it's stylistically preferred to just not have a bunch of global variables. Is like one reason I can think of off the top of my head. I guess, Ryan, is there anything else you'd say to that?
Yeah, if you want to have these as global variables, you need to know exactly how much memory to reserve in advance. And in this particular case, this program only has a single counter. And so maybe it's not so bad. We know that there's a single counter and we can make a single global variable. But if we're trying to generalize this into code that can be run multiple times, maybe at the same time, maybe there are multiple counters for multiple different flights, and we don't know at compile time how many different flights there are going to be. And so we need to be able to support an arbitrary number of counters. Then global variables actually fundamentally don't work at all because you have to statically allocate that memory, and we can't do that.
Exactly. Does that answer your question? Okay, so just for like time constraints, just to make sure that we have enough time so people can ask questions, I'm not going to manually type out everything, and I'll just show y'all like sort of like the finished example of how we'll do this in Rust. But before we do that, so I'm just going to sort of just like go through it like piece by piece right here. I'm going to introduce you to some new types. So there's this thing called an arc, and there's this thing called a mutex. And mutex in Rust, I think it's kind of a misnomer because it's a little bit more than a mutex that you might be familiar with, or a mutex that Jerry has talked about. So the mutex in Rust, I'm just going to highlight a piece right here. It takes in, so it's a container type. You can think of it as a container type, like for instance, like in the sense that vector is a container type, or box is a container type, or really ref cell, right? Ref cell, I think, is the idea that you should compare it to, right? So like before, when we would have used RC and ref cell, here we're using this other kind of RC called an arc, which I'm going to talk about in a little bit, and we're using mutex. And what mutex does is it's essentially It's a container for a piece of memory, and it ensures that you can have exclusive access to that piece of memory, right? A good thing to think about would be, okay, first of all, like, why do I need to wrap my mutex in an arc, right? So before we jump into that, let me just describe the semantics of this a little bit more. What lock will do, when you call lock on a mutex, is it will return to you a reference to what it contains. So you can safely modify that you can modify, what it's pointing to. You can read that value safely because you have exclusive access to it. The way it's implemented, it uses unsafe Rust, which we'll talk about later in the course, but that's how the semantics work. Can somebody explain why we can't just do this? Like, what would happen if I just passed in a mutex? So recall that this ticket agent function is being called in a loop. What if I just passed one, so this I think goes back to just the previous question of why is it that, we can't, why do we need RC in the first place? What if I just took away this reference counted pointer?
Can you show what the code would look like in main if you did that?
Yeah, sure. So then the code in main would look like this. Instead of, right, that's what it would look like. Right, and we'd no longer be able to do this clone anymore or actually would we? Do y'all think the mutex implements clone? Okay, so I see Trip, you're shaking your head no. Why not? Is it a can even go if I search up Rust mutex, we can even check on the documentation if it implements clone. Wow, that's disgusting. What happened there? That's crazy. Okay, but here we'll do a little sort of just how do we read the documentation together? I don't know if you've explored the docs much. You definitely should. It's great. It's beautiful, first of all, right? But they have examples and stuff. But if we look at trait implementations, it's great. It tells you what traits they implement. Because we talked about traits, you're now an expert, right? We know what debug is. We know what default is, what drop is. Well, actually, we didn't talk about default. But that just says that there's a way to have a default implementation of this struct or this object, right? And notice we have these things called send and sync, which the compiler was yelling at us about earlier, but we don't have clone, sadly, right? So that's unfortunately not a thing. So let's go back here then, I guess, right? So clearly we can't just do. So are there any questions about why we can't just have a mutex by itself like this? That's a great question. So I think we had that over here. So we tried to use RC, and it said it cannot be shared between threads safely, right? And now we want to think about, okay, I guess could you think of a scenario in which this makes sense, right? So what is an RC doing? For instance, what does an RC do once it goes out of scope? Yeah, it decrements the ref count. And how many assembly instructions might that expand into? More than one. And what does that mean? What if I have two threads and they both die at the same time? And they both are holding on to an RC. What's going to happen? Well, it will destruct, right? But as you said, that drop is going to cause a decrement, right? So you have these decrements happening from two different threads going on at the same time.
I think maybe Drew was trying to say that the memory wouldn't free, because what could happen is if you decrement at the same time, then you might have like the ticket sellers example where it underflows and goes to the top, and so now the reference count is huge, and the memory never ends up getting freed.
Sure. I mean, yeah, that's totally something that could happen too. I don't know enough about the internal implementation to know if they do like a check for underflow or something like that, or if they just assume that it will never happen. But the issue here is that this decrement can happen at the same time, right? And like the fact that this ref count can't be safely, there's nothing telling us that this ref count is being updated, that this ref count update is being protected by a lock. Do you know what I'm saying? So does that answer your question about why we can't use like a regular RC? So it wouldn't be so much as like one assembly instruction, because we can't really get around the number of assembly instructions you expand to, but this has more to do with it protects its update with a lock. It protects its update with a mutex, and it will do this, like the underlying implementation will use some sort of unsafe Rust to do that, right? So that's how we make things atomic, because oftentimes we can't control how many assembly instructions things expand out to, but we can control exclusive access, and we can enforce exclusive access using this lock. Does that make sense? For sure. Yeah, but that's a great question. Did that make sense to everybody else? Are there any questions about why? Yeah, that's a great question. So let's go back here. So if we just had mutex, what would happen, Julio? Right. Okay. Great. So let's look over here. What's going on here? So we have this remaining tickets ref, and this remaining tickets thing. We're gonna clone a mutex, right? So let's think about. So what are that? Okay, it's bad, right? Yeah. Right, that's a great question. So if you remember our example with RC, when we clone an RC, we're updating a reference count. So the reference count gets bumped up. We have an extra pointer to a piece of memory, right? But that piece of memory, it's still one piece of memory. We're still pointing to the same piece of memory. Yeah, in retrospect, I should have probably had a diagram for this. But I mean, actually, yeah. I mean, does that answer your question? Right. So like before, like we'd have to clone the mutex, but now we're cloning a reference to the mutex. So instead of having like two mutexes, or actually, sorry, I'm going to pull out my iPad real quick, and I think I'll just sketch this out, because I think that might actually be better.
Yeah. RC and ARC do some funky magic so that when you clone an RC or you clone an ARC, it doesn't actually clone the thing. Like you don't get a separate copy. What it does is it returns you a handle to the RC, which is linked to the underlying heap memory. So it still has the same underlying heap memory, but it's just bumped the reference count on it and given you a reference to it.
So like before, what would happen is you'd have like a mutex, and then you'd like clone it, and then you'd have like two mutexes, right? Can everybody see this? Right, and that's bad. We don't want to have two mutexes, right? Like that's not good. But now if we have a mutex, we have sort of like a mutex living inside of. So we have like mutex, and that lives inside of an ARC. You can sort of have. We can have like a reference to it in a way. So we can have like, we can have like reference 1. And then if we clone this, and then now the ref count is 1. The ref count is 1. Okay. And then if we clone that, then we're going to have reference 2. Bam. And the ref count gets bumped up to 2. And then if I want to spawn off another thread, I can have like reference 3. And then this gets bumped up to 3. Maybe this one goes out of scope, so this gets bumped back down to 2. So does the difference between these two pictures make sense? So like earlier, we would try to clone the mutex, and that's bad. Now we have one mutex, and we have a bunch of references referring to the same mutex. And because we have a bunch of references referring to the same mutex, we can safely, we can clone these references. We can have multiple things pointing to it, but once we actually try to access this mutex, we'll need to acquire a lock. We'll need to have, in order to have exclusive access to it. I guess with these two pictures, are there any questions about these two pictures? Awesome. Yeah. Do you have any other questions about like this in particular, or does anybody have any questions about this? Okay. Okay, great. In retrospect, I should have included something like this in the slides. But yeah, no, these are great questions. So to bounce back to this issue, so are there any questions now about why we can't just use a mutex by itself? Okay, so let's wrap it in this arc thing. So this arc is an atomic reference counted pointer. So we'll do arc new of mutex new. And then back here, this is going to be an arc again. So it's going to be an arc of a mutex. And then I just want to point some things out to you about how this is used. So this is us initializing that mutex. And this is us having a threads vector. So this is a vector of handles, so we can wait on our threads. And what I'm saying here is I'm saying I want to clone this reference. So this is the second picture that I drew, right? I want to clone a reference, and then I want to push this thread. And this thread is going to call ticket agent with I and with the remaining tickets ref. And notice how I do move, right? But the nice thing about move is not going to get rid of this, right? It's not going to move in anything that we care about, anything that needs to be shared. It's moving in this cloned reference. So it's moving in remaining tickets ref, and then we just wait for all the threads to finish. So about this, are there any questions about that highlighted piece of code there, about what's going on? I totally expect there to be questions. This is super confusing. This is super weird. You can totally put other data types inside of a mutex, right? So we'll see an example of that, I guess, like a little bit later in lecture, where you can even put structs inside of it, right? So in threading, there's this, and this is really nice because notice like kind of like the beauty of this approach, right? It used to be like the hardest thing about multi-threading is the fact that mutexes and the data they protect are kind of like disjoint from one another. And I don't know, like, since y'all have just learned this in 110, this might not be like quite as apparent yet, but it's like the way a mutex works, or like the data it protects, is defined by how you use it. It's defined by where you lock and unlock. But the beauty of this approach is that locking your mutex is acquiring the data that it's protecting. That's what this line here is showing. So I'm going to highlight this line. I'm going to break it down a little bit. Remaining tickets.lock is going to return some sort of result type. That's why we have to unwrap it. And it's essentially going to wait until it has exclusive access to this piece of data, and it's going to give to you a reference to that piece of data. And now that we have this reference, I can say, okay, if it's equal to 0, I'm going to break. I can safely make this check. And then otherwise, I'll handle the call, and I'll decrement the reference. I'll say I sold the ticket, and if I should take a break, I'll take a break. So, early, like with C++ and C mutexes, they weren't at all tied to the data. But now it's totally tied to the data. And the nice thing is there's sort of this, sometimes you want one lock to be associated with multiple pieces of data. This is, I don't know if like Jerry's like talked about, this is kind of like called like a monitor like model. It's like a term you might hear thrown around. If that term's like doesn't make sense, that's okay. But that's essentially saying, this kind of forces you to program in that style. This forces you to make explicit like what data is this lock protecting. In C and C++, that's just implied by how you're using it, where you're locking and unlocking. Here, it's much harder to shoot yourself in the foot because you have to say, okay, this mutex is protecting one thing and one thing only. It's a usize. Does that answer your question, Courtney? For sure. Please, yeah. Exactly, yes. It's exactly like a lock guard. So I don't know if the people who are currently taking 110 have seen lock guards yet, but it's essentially, so C++ also has an idea similar to this, but it's not as rich as that you can tie your piece of data exactly to the mutex. It's that you can define an object that when it goes out of scope, it will automatically unlock things for you. And this is like a very common error people make with multi-threading. They forget to unlock things, or they don't like do a bunch, like maybe there's like an if check that happens somewhere and you return from your function, but you didn't unlock before you returned or something like that. So exactly like you're describing, Trip, once this thing goes out of scope, and it goes out of scope at the end of this loop iteration, it will unlock the mutex, and it will allow presumably another ticket agent to have access to this piece of data, to read from it, and to decrement it as it desires. So I don't know if like stylistically people use, if people like explicitly unlock it. I think if you want to minimize your critical section, you can define braces and you can force it to go out of scope, but we can actually just look at the docs here, right? So what methods are implemented? You have new lock, you have try lock, which I assume is a non-blocking version of this, right? Which could be useful in certain contexts. Is poisoned is that's interesting. Get mute. So they actually don't it looks like they don't really have an unlock, which I mean could be good, right? But like if you want to force your critical, but like this is nice because this makes your critical section explicit. You have to denote your critical section with like an open curly brace and a closed curly brace, and then that I think that you can make the argument that stylistically is better. Yeah, I guess Ryan, do you have anything to say to that?
Yep. No, that's a. If you want to lock early, then you wrap the lines of code that you want to have the mutex inside of curly braces, so that when you hit the end of the curly braces, the that remaining tickets ref goes out of scope, and so it gets unlocked.
Right. Great. So are there any other questions about how this mutex thing works? No, I'd say it's actually the loop. It's this curly brace. It's this one. Sorry, I can't highlight to save my life. That one and that one. That is the scope of this. So by the end of this loop iteration, it will go out of scope. But that's how it ought to be, right? Actually, I mean, so like I guess like one thing to consider here is that maybe here we might even want to like minimize this a little bit more, because if we're taking a break, we don't need to hold on to the ref. Right, so I could even say something like, like that. I guess hopefully syntactically, I hope it doesn't get angry at me for saying this. But like this is also like totally allowed. I don't know. Will it let me? Okay, it doesn't let me auto indent. There's like this Rust format thing. But yeah, let's just sort of see how it feels about that.
Definitely fix your indentation if you're in a real editor.
Please do. But this isn't a real editor. But yeah, sorry. I just noticed there that this take break, it doesn't need the lock there. So our critical region only needs to be minimized to here while it's reading the value, checking it, and while it's updating it. But this take break doesn't need that. So before it was actually more sequential than it needed to be. But yeah, let's take a look here. So, wow, look at that. It goes from 249, 248, 47. Wow, that's perfect, right? There's nothing crazy going on. And then eventually it keeps going, and bam, all the tickets are sold, and they go home. It's the end of the business day, right? And yes, in real life, we would indent this to make it pretty. Or you could also just like sort of define this like update function in a separate, like if you think that this style is like so egregiously bad that you don't like having braces inside of braces, what you should do is you should actually have a decomposed function that will handle this, right? Because like I think from a stylistic standpoint, that's even better, because then this function by itself is atomic, right? This function by itself will acquire the lock. And the nice thing is that the user of your function doesn't even need to know that like there's like really, they don't have to worry about the fact that there's a lock in the first place, right? Because your function is handling that. Yeah. Does that make sense to people? Okay. So in the last couple minutes, I want to introduce a new example that we won't have time to get to today, but just to like sort of motivate. So like this is kind of like maybe a little bit of a contrived example, but one of the reasons we like multi-threading is because it helps us with a lot of I/O bound operations. So like when we're like reading, for instance, right? Especially from like network requests. So I'm going to switch back to the slides. I guess something I also wanted to talk a little bit about was this. Okay, another thing I wanted to mention is that there's deadlock danger. Remember, if we had like cycles of references with RC pointers, we could have memory leaks. If you have similarly, if you do your locks in a bad order, you can have deadlocks. So Rust doesn't always save you. This is one of the ways in which it doesn't save you, and we'll review this next time. We could even show you an example of a deadlock that happens in Rust. Send and sync. This goes back to one of Drew's questions earlier. So I don't want to like dwell too much on these two concepts, but it essentially says that. So send says that you can safely move between threads, right? And this had to do with the fact that with RC, like if regular old RC, we can't safely move that between threads because if you tried to update the reference count at the same time, you'd corrupt the state. And sync lets us have something get referenced from multiple threads. So the important thing to remember is that these are just marker traits. They're symbolic, and these safe threading constructs, or I guess like these standard library threading constructs that under the hood do unsafe things, right? They both implement sync and they both implement send. Don't worry, we can like review this next time as well, and you're welcome to like ask questions. I just want to introduce sort of there's this fun game that people have been playing, I think, where you're like on a Wikipedia page and you try to like click on links and like you try to start at dysentery and get to revolver or something like that. Like this is apparently a thing. And say we want to do a version of this game where you just start at a random Wikipedia page and you try to find a link to another Wikipedia page that is the longest, right? So like, can I find the linked page that's the longest, right? And if you wanted to do this sequentially, this is the most straightforward approach. There are no threads, there are no race conditions. So like, let's see how fast it is. So just want to do a quick demo here to finish this off. Wait a second, I want to actually open up this one. Oh wait, no. I have a tmux window open. Shout out to Ryan for introducing me to the magic of iTerm integration with tmux. It's quite lovely. But so we have this piece of code here that I'll just quickly gloss over. It reads from a particular, so this get, it'll essentially download a web page. It'll download the HTML. And this particular one is about multi-threading, so it's very meta. And then what this does, it's going to filter out all of the links. So don't worry too much about the syntax. I'm just going to describe at a high level. This is filtering out all of the links on the web page. And then we're going to go through each of the links, and I'll actually print it out here so you can appreciate how horribly slow it is. It's gonna go through all of the links, and it's going to update a running tally of like, okay, what has been the longest URL, what is the longest article so far, and what is the length of that longest article. And then if the current length is greater than the longest length, then we update it accordingly. So let's actually just run that. So I'm gonna do a cargo run right there. And let's just see. Oh wow, that's even, okay, that's like slower than I was expecting.
Did you save the Vim buffer?
I'm pretty sure I did. Oh yes, thank you. That's exactly what it was. So it's rebuilding. So we have to wait for. So now we have to wait for the slowness of the Rust compiler and for. Okay, great. Wow, look at that. Look at it. Look at it zoom through all those links. Like wow. So there are a lot of links, is what I'm saying. And when I timed this took roughly 3 minutes to get through all of them. That's the sequential version. Okay. Now I'm going to go over to the multi-threaded version. If I go to Link Explorer Multi, so it took 3 minutes sequentially, and now if I run here, so you might be wondering, okay, this is pretty slow too, but like that, it's done. And it was able to find out that artificial intelligence, rightfully so, was the longest article with this length, right? So no matter where you start, even if you start at multi-threading, somehow all roads lead to AI, which I think is a meme. But or, I don't know, like that idea that everything just like goes into, I don't know, it's kind of funny, I think. But yeah, so like the idea here is that we can zip through things really fast by multi-threading. And you might be wondering what this batch index is. Because we're at the end of lecture, we'll save that for next time, like that explanation there. But I just wanted to show you this one last slide, just comparing the times, because I actually did time it, and the times are pretty devastating, right? So like with the multi-threaded version, so sequential was 2 minutes and 55 seconds, multi-threaded was 9 seconds. So that's crazy, right? So you definitely win a lot by multi-threading because you're able to overlap the waiting times for all of these I/O operations, and that's powerful. So next time, in addition to just wrapping up some of these ideas, we'll talk about other synchronization primitives, and then next time we'll talk about approaches to concurrency that go beyond shared memory. So yeah, thank you all so much for coming to lecture, and please stick around if you have questions. Great, yeah, okay, so let's talk about that again. Maybe the choice of ARC over RC. I'll actually try to draw a picture for that as well. I think that might be helpful. So I'm going to stop this share, and I'm going to go back to my iPad. And then let me just do another share right there. Okay. This is always such a process. Right, so this picture was justifying why we need to wrap our mutex in an ARC. Let's think about what could happen with RC. So if we had RC, right, if we had like, so what I'm drawing, this box here is like RC's underlying memory on the heap, okay? So this is like the RC, and this is like the ref count, and currently there's one reference to it. There's this reference 1 pointing to it, so reference 1 is pointing to it, so the ref count is 1, okay? And let's say we generate reference 2, and then we move this into thread 1, for instance, right? So now the ref count is 2, okay? And then we have reference 3, and then we move that, so, and these are generated by cloning, okay? And then we move into thread 2. Okay, so we have like, say like, this is thread 1. I can't write. Okay, this is thread 1. And this is thread 2. And then at the same time, because the scheduler is just really malicious, I guess, they both drop these references. So this says ref2.drop. So remember, the drop function gets called once it goes out of scope. And then thread 2 says ref3.drop. Right? But this happens simultaneously, right? Or sorry, I don't know if that's like the right way to say it, but like, yeah, so like these two things happen at the same time. And then this drop, so like this drop is going to do what? It does something like ref count minus equals 1. So could you see something that might go wrong if both of them try to decrement at the same time? There totally will be a race condition, exactly, right? It's the same race condition that you actually saw in the ticket agent example that Ryan introduced last lecture, right? Because there are all these ticket agents trying to like decrement this like shared variable, this counter, right? This ref count is also a counter, and if these two threads try to decrement the counter at the same time once they drop these references that were moved into them, then we're gonna have a corrupted state. And then, you know, like maybe like the ref count gets really big or something random like that, and then we have a memory leak or something of that nature. So we need this update to happen atomically, and that's what ARC gives us. So to transition, we'd say like, you know, arc does this update atomically. Do people know what atomic means, by the way? I don't know if Jerry's talked about it yet. I guess, can someone give like a good definition of atomic? That's exactly right. So like it's all or nothing is the way I like to think about it, because so it's either like this decrement happens or it just doesn't happen, right? It can't go halfway through. And it going halfway through is what leads to problems, right? Because that's when you have like two ticket agents trying to like decrement that counter at the same time, because one got halfway through its operation and the other one like started while the other was halfway through. Precisely. So when this gets dropped and when this updates this reference count, it will acquire a lock before it does the minus equals, and then it will release the lock afterwards.
Okay.
Yeah, there are also some CPUs, such as x86, that have single instruction increments or decrements. They're called atomic integer, not integer, but atomic number instructions. And so because it's just one instruction, it can't be interrupted. But on systems that don't have atomic instructions, then like Armin mentioned, it will use a lock to protect it.
But what if it doesn't live in a register, Ryan? Don't you have to like read it from memory, and isn't that like multiple instructions?
Yeah, but there's a special instruction for doing an atomic decrement or increment on a memory location. And they're slower than using the normal like read into a register, increment or decrement, and then write back, which is why you wouldn't want to use this all the time. It's only something you want to use if you actually need to use it, but those instructions do exist. And so on CPUs with atomic support, they'll use those instructions.